Hey guys, here today to talk about section 3.5, which has to do with systems of equations with three variables. Now we've talked a lot about systems. We've seen elimination, substitution, graphing as ways to solve systems. We're going to be using those same strategies, but now we have three equations and three unknowns, x, y, and z. So I stole this graphic from your book, but you can see here there's still three possibilities if we have a system of three equations, three unknowns. It's possible we have one solution where all three of these planes now, because we're in three dimensions, because we have three equations, all three of these planes intersect in one point. It's possible that we have infinitely many solutions. So for example, if they all intersect in this line that goes up and down forever and ever and ever, well, then there would be an infinite number of solutions. Or if two of the planes were exactly the same and they intersected the third, that would also be infinitely many solutions. There's also this idea that there could be no solution, just like we saw in 3.1. Maybe all these planes hit, but they never hit in the same spot. Maybe two of them are parallel and they hit the other one, the third one, but again, they never hit in the same spot. Maybe they're all parallel. It could be that there's no solution. Now, when we're talking about ways to find these, put a little note at the bottom, these ordered triples, we call ordered pairs when we have x comma y. So now we have x comma y comma z, ordered triple. When we're talking about ways to find these, graphing is probably not going to be the way to go because as we've seen here, we're graphing in three dimensions, which is hard, which is just hard for our brains to handle and see and really truly process. So we're going to be using substitution and elimination as our way to solve these systems of three equations and three unknowns. So here's the general strategy. I'm going to recommend, and it's possible to do this with elimination, but I'm going to recommend you always start with substitution. Okay, you always start with substitution. And that's what I'm going to demonstrate. It comes out a little cleaner, fewer mistakes are made. So we're going to use substitution to get our system of three equations down to a system of two equations. Because once we have it down to two, I pulled this from a previous section in our notes, we know how to solve a system of two. Here, I used substitution again to get it down to a system of one equation with one unknown, with only y's over here. So we have lots of strategies for dealing with systems of two equations. If we can just get our systems from 3 to 2, then we're good to go. We can use substitution or elimination at that point, solve it, plug stuff back in. Let's see an example. So example states pretty simply, find x, y, z, find that ordered triple. We've got these three equations here. So with what I said earlier about always start with substitution, I'm looking at this and I'm looking for an easy variable to get alone. This minus y wouldn't be too bad. X, it's already positive, that's nice. Y is already positive, so that one's nice. Negative z isn't too bad. Just like we saw in 3.2, it doesn't really matter which one you start with as long as you're being careful with all your arithmetic. I'll go ahead and get this y on bottom by itself. So substitution, I need to isolate one variable. I'll go ahead and do that. So y is equal to negative 5x plus z if I add it over, plus 14. Okay, so at this point, I kind of structure my work maybe a little uniquely, but I like to keep that in one column. I got y by itself, I half boxed it because I'm really going to need it later. Now I'm going to come over here and I'm going to plug that y into my other two equations. So 2x minus what I just found for y plus 3z equals negative 2. This should look really familiar, really similar to the substitution we've done earlier this chapter. So negative 5x plus z plus 14. And then let's simplify. Let's distribute, let's combine like terms. 2x plus 5x's minus z minus 14, but then plus the 3z's equals negative 2. So 7x it looks like plus 2z's if we combine the z's, minus 14 equals negative 2. And I like to just get it in sort of standard form looking 7x plus 2z equals 12 when we combine those constants on the right-hand side. So just plugging in y to our first equation, and then now I'm going to do that to our second equation, x plus 4 times my alternate definition for y minus 2z equals 16. So alternate definition was negative 5x plus z plus 14. So x minus 20x's plus 4z's plus 4 times 14, which happens to be 56, but then minus my 2z's equals 16. Same thing, let's combine like terms. So negative 19x's plus 2z's plus 56 equals 16. Subtract 56 on both sides. Negative 19x plus 2z equals negative 40. Okay, so again, I'm half boxing everything that's really important that I'm going to need later. So I'm going to draw another dividing line because I want to start a new column of work. And here, what do we need to do? Well, we need to somehow figure out how to take our new two equations with two unknowns. Notice we got rid of the y completely. We need to figure out how to take our two equations with two unknowns and solve it. So to solve this system, in my third column, I'm going to write them 7x plus 2z equals 12 and negative 19x plus 2z equals negative 40. And I like what I'm seeing. At this point, I said start with substitution always, but here I can use substitution or elimination to solve this. And it looks almost tailor-made for elimination. We've got this 2z match, right? So you could use substitution here, but I'm going to use elimination. I'm going to subtract my second equation from my first because I know that 2z minus 2z will be gone. So what is 7x's minus negative 19x's? If you need to, you can pull out your calculator. 7 minus a negative 19. So 26x's equals 12 minus a negative 40. Remember to subtract that negative 40. We're subtracting the whole equation. 26x's equals 52. Well, what would 52 divided by 26 be? If we divide by 26 on both sides, we get x equals 2. That's almost like a 3/4 box. I mean, we're getting close. We found x. So now how do we go and find z and y? We're just going to work backwards now. And so that's why I like making my columns. On the way there, I'm working all this way until I get to a point where I find a value. X equals 2. That's great. Sorry, going to close out something that just popped up on my screen. X equals 2. Let's go ahead and work backwards now. So coming down here, I can plug that x value into either one of these two equations. I'll just do the bottom one because it's here. Negative 19x plus 2z equals negative 40. And x, we are saying, is 2. So that means negative 19 times 2, negative 38, plus 2z equals negative 40. Let's add 38 on both sides. So 2z then equals negative 2, because negative 40 plus 38. Divide them both by 2, z equals negative 1, it looks like. And now that I have that, I have x and z, I can just plug them into my y equation. Y equals negative 5x plus z plus 14. So negative 5x we said was 2. Z we said was negative 1. So we're saying that y equals -10 minus 1 but plus 14, -11 plus 14. It looks like y equals 3. And it really at the end of the day looks like x comma y comma z should equal 2 comma 3 comma -1. Now you're looking at the screen, you've been following along and you're saying that is a lot of work, and you're not wrong. It is a lot of work. Systems of 3 equations, there's a lot of steps. But one thing I would point out is that none of these steps was really anything new, if you will. I mean, sure, we've never done one with 3 before, but we got y alone and substituted it. And then we had combining like terms to do, but we've been doing that for a while. We take our 2 new equations and we used elimination. And then once we got x equals 2, we just started plugging stuff back in, working backwards. So I like to structure my work like this because it's just this pattern that my mind remembers where we go down, and then once we get x equals 2, we get our first value, we go back. And at the end, we will have values for all 3 of these. Now notice I haven't boxed my answer yet because there are a lot of places I could have made a really silly mistake. And so what I'm gonna do is I'm gonna be sure to check all of these answers. I'm gonna use my calculator. I'm gonna say 2 store in x, 3 store in y, -1 store in z. And now when I start plugging in, typing out my original equations, I'm really hoping that they all work out, because otherwise I need to backtrack and see where I made a silly mistake. 2x minus y plus 3z equals -2, which is exactly what it says it should in that top blue equation. Okay, so 1 down, 2 to go. X plus 4y minus 2z, 16, 2 to go. Type in the last one, and please, oh please, when I say 5x plus y minus z, please be 14. And it is, and that's kind of the best feeling, because again, if we had made a mistake, it could be buried anywhere. We have to go back and search and try to find it. And then if we search and we can't find it, we might just have to start over and start from scratch. But being super careful, super precise, we find that x, y, z equals 2, 3, -1. We checked all our answers. You know, we dust off our hands, we go home, we call this one good. Okay. Couple other variations. Now, I have a note here that says before starting, always seek to reduce your equations if possible. If there's something we can divide out of all of them, yeah, let's make our lives easier, the numbers smaller. So we've got these 3 equations. We're solving for A, B, and C. And so here's what I'm looking at. Before I start my columns, I'm gonna say, it looks like I can divide 2 out of each of those. They're all even numbers. So I'm gonna reduce this equation to make my numbers easier to work with. So divide by 2, 3a plus 6b minus 4c equals 12. It looks like each of these on the second equation are divisible by 3, right? So 3a plus 6b minus 4c equals 10. And it doesn't look like I can divide anything out of my third one, not out of everything. So 4a plus 8b minus 7c equals 26. Reducing your equations before you start has an added bonus. It makes our numbers easier, smaller, easier to work with for sure. But here's that added bonus. From here, we can see that this system of 3 equations has no solution. And here's my justification for that. 3a plus 6b minus 4c has to equal 12. That's what red says. But right below it, 3a plus 6b minus 4c has to equal 10. There's no way that we can get 12 and 10. I mean, it can't work. These are parallel planes, kind of like parallel lines that just equal a different thing on the other side. Left-hand side's all the same. Right-hand side is not. So once we reduce our equations and we see this, it is enough to say, you know what, no solution. And that one was a lot nicer than the one above. In some ways, I like having a solution, but it was a lot less work, a lot less time consuming. So always reduce your equations. And if you get something like this, two equations that are exactly the same on the left, but have different rights, different constants, you know it's no solution. Those are parallel planes. All right, how about this one? Solve for x, y, z. I'm gonna look to reduce and kind of simplify my equation. So that top one in red, I think I can reduce everything by 4. So I'll say 2x plus 3y minus 6z equals negative 10. And then I don't think I can reduce this second one because that 3 and the 8, there's nothing that go into both of them. So 3x minus 8y plus 12z equals 23. And the third one, 2x plus 3y minus 6z equals negative 10. There's nothing to reduce there. 2 and 3, nothing to reduce. So again, just making our numbers easier and now seeing if we can spot any patterns. And in fact, we can. If you look at these two equations I'm circling in green, they're exactly the same. They are exactly the same plane. And so it's kind of like when we had those dependent systems when we had two lines that were the same and they just were right on top of each other. That's what we're looking at here. We have two planes that are exactly the same. So the only question is, does this mean infinite solutions or does this mean no solution? Because these two intersect, and I'm going to try to show this on the screen. These two planes intersect. They're the exact same plane, and so they're kind of right on top of each other. But what if the third one is parallel? Then there's still going to be no place that all three of them hit at the same time. Luckily, we know what parallel planes look like. We saw them on the last one, where the left-hand side with the A's, B's, and C's is all exactly the same, but the right-hand side is different. So that's all we have to check, and a quick glance says, no, that other one, 3x minus 8y plus 12z, that's not going to be parallel because it's not even close to the same on that left-hand side with the x's, y's, and z's. So that means these will intersect somewhere. Here's my first and third plane maybe that are exactly the same. Here's my second one. And it's going to intersect all along this line where my fingers are meeting my palm. And so this is infinite number of solutions. If you can look at your equations and you find two that are the same plane and you know they intersect with a third, that they're not parallel, then definitely infinite number of solutions. All right, last problem, word problem. I'm gonna go ahead and set this up and we'll set it up together, and then I'm gonna pause and let you kind of try to work this one on your own. I will tell you this is not no solutions. I will tell you this is not infinitely many solutions. It's kind of just your standard typical one solution, find it. So here's what we say. Jambalaya is made from chicken, sausage, and rice. Simone is making a large pot of jambalaya for a party. We're told that chicken costs $6 per pound, sausage $3 per pound, rice $1 per pound. Spends $42 on 13.5 pounds of food. Okay, so you know what, I'm gonna actually circle this in blue. I'm gonna keep this red because it seems like it's still dealing with money, which is what I underlined before in red. She buys twice as much rice as sausage, and we need to find out how much chicken, sausage, and rice did Simone use in her jambalaya. Let's do this. Let's start writing out equations. Remember, we have three unknowns. We need three equations. So the first one I'm going to write, I think, is the money one. That's what came first in this problem. So 6 pounds of chicken plus, sorry, $6 per pound of chicken, I should say, plus $3 per pound of sausage, plus $1 per pound of rice should all equal $42 at the end of the day. That's my money equation. I also know that the pounds of chicken plus the pounds of sausage plus the pounds of rice need to add up to 13.5 pounds. So I've got two equations with three unknowns. The third one is the one that gets mixed up the most, and I mix it up all the time. Twice as much rice as sausage. So I got to be really careful how I do this. Twice as much rice means I have more rice. I have 2 times as much rice. So that means whatever my rice is, it's equal to 2 times the amount of sausage. And again, it's really tempting to say 2R equals S. But if you're not sure, here's how I think of it. Okay, twice as much rice as sausage. That means if rice was 10, sausage was 5. Does this match? Would 10 equal 2 times 5? Yes, it would. So we know we wrote the equation the right way. We need to double whatever amount of sausage that Simone bought in order to equal her rice. So these are our 3 equations. I want you to pause this video and try to solve this. We said always start with substitution, and that's a fantastic one to start with because R is already alone. So pause the video, start substituting, get 2 new equations with only C's and S's, and then solve that and work your way backwards. See what you get. Try this on your own. I'm going to pause and try it. But it's important to be working these things out on your paper and trying them get that muscle memory. So we'll both pause and then we'll both resume here in just a second. All right, I'm going to resume this recording because I've worked it out and I've got my work on the screen. So hopefully you can pause it if you need to, if you got something different than I got. But what did I do? You know, we started off, we wrote the equations we had. I worked it over here, plugged them in, got my 2 new equations, worked it here, and then used those 2 new equations. I ended up using elimination again because it seemed pretty easy. Used elimination, found S equals 3, which means now I'm on my way back. Plugged in 3, found C was equal to 4.5, and then plugged in S over there, found R was equal to 6. So it's a lot of elimination. It's a lot of, it's a lot of lines of work maybe, but again, it's things we know how to do. I went ahead and I checked all my answers, plug them in. You can use C and R and S, alpha, and then you see the entire alphabet written in green letters above a bunch of those buttons. So for example, alpha, and then this program button is C. So I stored the values in C, S, and R for chicken, sausage, and rice. It all worked out. It looks like the answer is 6 pounds of rice, 4.5 pounds of chicken, 3 pounds of sausage was used in this jambalaya. That's a lot of jambalaya. It's going to be a great party that Simone's throwing. So again, pause this and really take a good hard look at the work if it doesn't match what you got. See what's different. See if we can figure that out. If you have questions about this section, please bring them to me. The biggest advice I can give you, once you know the methodology, is just take it slow and be super careful, super precise. Make sure you don't mess up a negative because that'll mess the whole thing up. And if you mess up a negative over here somewhere, then it throws off the entire rest of your problem and then you have to backtrack all that way. So be careful, be precise, substitute, eliminate. If you have questions, write them down so you can ask them next time we meet. But other than this, guys, take a look at some of our practice problems. You don't have a ton because these do take a little bit of time, but it's just muscle memory. It's just working the problem and knowing what you're going to do, and your brain falls into that pattern so that you no longer have to think about how did I solve that system of 3 equations. So take a look at practice problems. Let me know if you have questions, and I hope you guys are having a fantastic day.